So another student asked me about question number 5, analysis and discussion. Based on your observed rate constants in trial 1 and 5, use the 2-point Arrhenius equation. Gotcha. Okay. So here's what I'm going to do. I'm going to come over here and I'm going to say 1, 5. I'm going to set up a key for myself because if I'm not careful, I'm going to get in trouble here. Temperature. And this is going to be temperature, and it's got to be in kelvins. Okay, I know that because this number comes from my Alex calculator. I think it's 8.314 joules. We'll look it up, but per mole Kelvin. I think that's what that is. And this number is going to be in joules or kilojoules. We'll have to make sure that's consistent. This is really cool. And then these numbers, we got those from our equations. We know what those are. Those are going to be molars, reciprocal 2, whatever. Reciprocal 1. But it's the same units for both of them, so those cancel. And so then therefore this needs to be in kelvins. Okay, great. So let's go look at it. The temperatures was, the temperature for 5, that was the cold one, was 0. In kelvins, it's going to be minus, or rather positive. Okay. And positive 273.15. And in the, because it was frozen, right? And in the temperature for the other one, what was the temperature? We have it up here somewhere. The temperature was 22.5 degrees Celsius. Only 2.5 and 22.5 plus 273.15 equals, oops, I don't mean this. I didn't spell that right. How do you spell 273? Like that? Okay. So it's going to be 295.65. And of course, that's the last digit that I can report. I'm going to use all the digits, of course, but this is really 4 sig figs because when you're adding or subtracting, right, you can only add 2 precision. Okay, let's go look at the K's then. I remember the K for the K for the 1 was 239.65 because I just looked at it a minute ago. Let's look at the K for, what was the K for the cold one? There you go, 156.72, 156.72. Okay, great, awesome. We're ready then, aren't we? So in that case, this is going to be the natural log of those two numbers is equal to e to the a over r, which I have in my Alex calculator, times 1 over t2 minus 1 over t1. What I'm going to do, I'm going to rearrange this first. I don't want to, really this is what I'm looking for, right? I'm looking for the activation energy. By the way, this is supposed to be minus. I just realized I just did that. Okay, minus. So in order to get the activation energy, let's go ahead and solve this. This is going to be, if I multiply both sides by r, it's going to be r times natural log of that fraction, which we'll fill in just a minute, is equal to minus EA times that difference of 1 over T1, 1 over T2. I'm not writing these in. You want me to write those in? T2, T2, T1, T1. These are numbers I have over in my key, right? K2, K1, K2, K1, right? Okay, so now I'm going to divide both sides by that difference, okay? And it's just going to be a little bit ugly. Can I just say it? Just divide it right here. 1 over minus 1 over. And then get rid of it from that side. T2, T1. And actually, you know what else I'm going to do? I'm going to make this a plus and this a minus. Okay, and now we have solved then. Okay, we've effectively solved for EA. So let's do it now. Let's come over here and I'll put all the numbers in. The activation energy is equal to minus R, which I'll go look that up in a second, times the natural log of these guys, of that fraction, divided by 1 over okay, and R, let's go look up R. Okay, actually I'm going to do it in my Alex calculator. I love these Alex calculator. It is so effective. Watch. I'm choosing the old topic here. And we'll open the Alex calculator. Okay. And so it's going to be, let's go back over here. It's going to be minus R. Okay, let's do that. Oh, it's a big fraction, right? So I'm going to do a fraction over parentheses over parentheses. Parentheses over parentheses. Okay. And in the bottom, I'm going to do 1 over minus 1 over, right? You see how I'm setting myself up first? Okay, this is R times natural log of K1 over K2, right? Okay, so I'm ready to do it now. And this is a minus R. So if I come over here, and this is my R, which is my Rydberg energy. Nope, it's my gas. It's my Rydberg energy. I guess you got to know that, don't you? Yeah, that's what it is. Yeah, you got to be told that. Are we told that in the question? Let's go look. Oh, there it is right there. No, it's not Rydberg energy. It's that. Okay, we got it. Never mind. That was about a mistake, wasn't it? 8.314, it's still here. It's that one right there. 8.31446. Right? I think this one gives it to you with less 446 with less precision, but let's go with the one that's in the Alex calculator. And so, and then it's going to be K2, and K2 is 156.72. Divided by K1, 239.65, right? Divided by T2, which was 0 degrees Celsius, 273.15, and T1. T1 was 295.65. 295.65. Okay, kind of ugly, isn't it? All right, wish I could see all of it at once, but let's just make sure we got it right. We got the lens, negative 0.83. This was going to be in, let's check our units too. So this is going to be in joules per mole Kelvin, right? That's the units of my 8.314. This is unitless, has no dimensions because they cancel. and this is reciprocal kelvins. So this is going to be essentially 1 over kelvins. So the 1 over kelvins cross off, boom, and boom, and so it's going to be joules per mole. All right, that's going to be in joules per mole. All right, so, and we got it. All right, so let's do it now. Let's go back over here and let's hit enter. And it's going to be 12,674, 1.2674 equals 1.2674 times 10 to the 4. Let's go with blue. Joules per mole. Okay. And I'm going to change that. I'm actually going to write this as, we also have to work with the number of sig figs, right? So it's going to be 1.2674 times 10 to the 1 kilojoules, right? So we would write that simply as like 12.77 or whatever, okay? Now let's go figure out how many sig figs we have here. These temperatures were each, that was 4 sig figs, right? Because it was added that, okay? So this is 4 sig figs down here. And what was it up top? That was dimensionless. Ah, with logs, yeah, it's difficult to say because the log rules for sig figs are weird. We don't use them enough to be good at it. Let's just say that there's 3. What were these K's? These K's. Oh, that wasn't 4 sig figs. That was 5 sig figs. These K's are. Let's go with 2 sig figs over here. I'll tell you later why I said that. 2 sig figs, and this is. That was 1, 2, 3, 4, and we used like 5 or 6 sig figs in there. Okay, 6 sig figs. Okay, so the answer is going to be really the 2 sig figs. So what we're going to do is we're going to say then that this is 13 kilojoules per mole. All right, neat problem. I spent a lot of time doing math, but this is really what I did was I just went and looked up these numbers and then stuck it in the Arrhenius equation. Okay, hope that's helpful.